A little better. Good afternoon, everyone. So just a few announcements. As you know, Lab Zero has been out there. It's due this Thursday. There are no late days, no grace days, no excuses. So don't put it off to the last minute. It should be, everything's set. You should be able to do it. Lab 1 became available sometime early this morning. And for starting with Lab 1, the way we're going to release the information you need to do is through this website called the Project Zone, which will guide you through the write-up and require you to answer some little simple questions along the way, is our way of encouraging you to read the write-up carefully. And only once you get through that, you'll get a little code. Now, you can actually start the lab and do all the work of the lab because you'll be able to get the files actually for it off of AutoLab directly. But to see the write-up and to actually submit it to AutoLab, you'll have to have this little pass key that comes at the end of your completion of the write-up through the Project Zone. And then you'll put that in a file and submit that as part of your handing. So that's all described, but there's this sort of two-phase part. There's the Project Zone and there's AutoLab both. This particular lab is will make use of what you learned last week and this week about bits, bytes, and numeric representations. And so in particular, a good chunk of the problems are just bit-level manipulation questions that the lecture material for it will be from last week and from today. And then on Thursday, we'll talk about floating point, and that will cover all the information. Then next Monday will be your first recitation class, and it will talk about that quite a bit more. But I'd recommend you get started before next Monday on this lab. Question over there.
So I did get a code, but I actually submitted my assignment for them without using the code. Is that only stuck for lab 1?
Yes, lab 0 does not require any code. In lab 1, by the way, I'm not sure if AutoLab is working quite right yet on as far as submissions. So if you're really out early and you want to submit it today, it might not work. We're tracking that down. But you can certainly get started on the lab as it is. This, and also mention, and I'll say this in the various other places, this particular lab has more kind of quirks and bumps and warts in the software than I feel good about. Let me just put it that way. And the reason is because we've kind of patched together this odd mix of software to support how we do the checking of your code for its conformance to some programming rules and correctness and things that as try as we might, there's some sort of odd aspects of it that are all documented in the write-up, but it's easy to overlook that when you're first skimming through. So this is one of these things, before you run off to Piazza and ask, what do you mean about this? Or what do you mean about that? Or I get the following weird error report. Please reread the write-up several times, because a lot of times all of a sudden it will jump out at you that you have to have a right curly brace in the first column to finish your function definitions that aren't part of the normal C programming conventions. So today we're going to continue talking about the representation of values, in particular integer values, as bits. And we started that last time, and what we'll do is continue that today, talking about the different arithmetic operations you want to perform on bits. We'll also cover some more general, the sort of how information is stored in memory and how it's referenced. So you recall from before that the two equations that you really have to know and understand, and everything else follows from those two equations, is given a set of bits, what number does that represent? And we can talk about that number as either an unsigned integer, meaning its value is either 0 or greater, or the other representation we'll look at in this class is 2's complement representation, which allows you to have numbers that are both negative and positive. And the way that works is by simply making the most significant bit have a negative value to it, so that if it's set, then it sort of makes the number very negative, and then you can add back some more bits, positive bits, to bring it back closer to 0. And so we looked at the example, and here's the correct version of it, that 10 is simply 2 plus 8, but minus 10 is minus 16 plus 4 plus 2. So you start with minus 16, you add back 4, that gets you minus 12, add back 2, that gives you minus 10. I should also mention 2's complement. There's nothing in the C standard. In fact, the C standard is very careful not to say, thou shalt use 2's complement numbers. But the x86 processors, which is what we use, and really just about every processor that you're likely to come across, does use 2's complement. So you can't always assume this when you're writing programs, but for the platforms that we're interested in, this will be the case. And so we talked about this idea that there's a sort of correspondence between unsigned and signed numbers that's based on this kind of odd idea that when you convert from one to the other, you actually don't do anything. You keep the bits in their whatever pattern they are, and you just change your interpretation of what those bits mean. So for these are 4-bit values. So as an unsigned number, it can range from 0 to 15. But as a 2's complement number, it can range from minus 8 to positive 7. And you'll notice that for the positive case, the place where these two representations overlap, they match. But for the cases where they don't, what is a very large number, a relatively large number as an unsigned, becomes a negative number as a signed number. But anytime a program in C casts or for some reason sort of switches between unsigned and signed representations, that's what it's doing. It's nothing. It's just changing what numeric value is assigned to a particular bit pattern. And that has its sort of strange and quirky behaviors to it. And the other that I mentioned last time, and is especially peculiar, is if you have an operation, say addition or less than, and one of the operands is signed and the other is unsigned, the rule in C is, and this is the C standard, is there'll be an implicit conversion of that signed value to an unsigned value, and then whatever operation be performed is performed. Last time we also talked about this idea of sign extension, which is to take a smaller bit pattern and make it larger. You do it by copying the most significant bit into the new positions. And what we saw with that is, for the case of, and this is for a 2's complement number, what it does is it gives you a larger number of bits, but it represents the exact same number. Similarly, if you want to shrink a number, what happens is they just chop off the high order bits, and whatever, if it's a signed number, whatever used to be in this, what's the new most significant bit position, that becomes a signed bit. And that may or may not be a good idea in terms of preserving numeric values. Obviously, if you're going to shrink the number of bits, some values will be unrepresentable, and that's the consequence of this. But that's just the way it works. So now let's look into arithmetic operations, and we'll see the same general ideas apply. That, and usually it's a little more intuitive to understand the unsigned case than the signed case. So the idea with unsigned addition is, in principle, if you want to add two numbers, each say of n bits, that to fully represent the sum of those two numbers, you might need n plus 1 bits. And it's a little hard if you keep adding numbers to go get more bits. And so what happens is we just chop it off and say, whatever the extra bit was I'm going to ignore it, the so-called overflow bit. Whether it was a 0 or 1, I'm not going to do it. And the effect of that is sort of a modular arithmetic, that the addition sort of just wraps around and continues on. So for example, this example shows if I add the numbers decimal 223 to 213, if I had enough bits, I'd get the number 446. But I don't. I'm going to keep it at 8 bits. And so I'm going to just chop off that most significant bit, and the result I'll get is 190, which you might notice is exactly 256 smaller than 446. And that's the effect, because you can think of here that we're dropping up that bit there that we're dropping has weight or value 256. And so by eliminating that bit, what we're doing is decreasing the result by 256. And so actually, and this is part of the C guarantees that all addition will be performed as modular addition. So even when it overflows, the program has completely well-specified behavior of what it's supposed to do. So if I think of the possible range of values that these numbers could have along the x and y axes, and then the sum of the values on the z, then sort of normal addition would give you this plane, diagonal plane, because, well, it's sort of the definition of a linear function. But if I go to 2's complement addition, to unsigned addition, what you see is it sort of splits into these two regions, each of which has a plane. And the left-hand part shows where it's, by the way, I'm going to try this little doodad today. This part here shows where it's the true sum of the numbers. But over on the right here, I don't know, it's technology, where it would have kept going up. Instead, what I've done is I've chopped off that most significant bit. This is 4-bit addition here, so I've chopped off the value of 16, and now what's left is the original sum minus 16, and so that will climb up, in this case, up as high as 14. So as the picture on the left shows, you can think of when you do the overflow, then you're shifting the sum back down into the range of the original set of numbers. So for 2's complement addition, part of the reason why it's the commonly used technique is the hardware is the same. The actual low-level addition operation is exactly the same for it. We simply add the two numbers and throw away any extra bits that might overflow and call that result the sum. And so as you, and this is an important thing to understand, is that whether you say it's a sum of two ints or a sum of two unsigns, the actual bit level behavior is the same. And again, you can see that here with the same set of bit patterns as before, but now since this is a 2's complement number, if you look on the right, you'll see that these bit patterns represent the numbers minus 23 and minus 43, respectively. If you were to just add those numbers, you'd get, as just bits, you'd get 446, which doesn't seem to make much sense. But if you chop off that most significant bit, you'll see that what you have left is the bit pattern for minus 66, which is exactly what you'd expect. Turns out if you really want to do 2's complement addition and add the extra bits, I should have sign extended it to be a 9-bit numbers and then done the addition, and then it would have come back here. So this is a little bit of a peculiar example. But you see that the result is this idea that now the remaining 8-bit number represents minus 66. So again, you can think of what happens is, let me jump to this picture. Well, no, I'll go through this picture. So now there's actually two overflow cases. What can happen is if you take two numbers and add them, and each of them is W bits, then if you look at the actual, what I'll call the true sum, the sort of mathematical sum of those two numbers, you have three different cases. One is that that result is within the representable range of a W-bit 2's complement number, in which case that's the result you'll get. But if the number is too big, then it's called a positive overflow. And what we'll see is it will convert it into a negative result. And then the other is if the number is too small, meaning too negative, then you'll have what's called a negative overflow, and the resulting number will end up having a positive value. So we can visualize it using the same idea as before, that this center region are the sort of non-overflow cases. They're the ones where the sum of these two numbers was within the range I could represent as a 4-bit 2's complement number. And the numbers that the sum would have been too negative are on the left, they become positive. And the numbers that were too large, too positive on the right, become negative numbers. So that shows those two cases. This is all, by the way, if you look at the formulas, it all makes sense. And once you get used to this idea, it becomes very routine. But if it's the first time you've ever been confronted with this, it might be fairly non-intuitive. And the only way I can advise you is look at exact little examples of 4-bit numbers, try adding them together, see what you get, compare that to the various formulas, check it out. That you have to kind of let this stuff bake inside of you to really fully appreciate it. So if I look sort of a bird's eye view from the top of that this picture here, you can see that there's sort of three regions. If I for consideration, the white region here is the case where there's no overflow. So that the sum of the two numbers is representable within the range of the result. And so that's the value I get. And then the two pink ones are the overflow cases. And you can see that, first of all, if you're adding numbers of opposite signs, you see you can never get an overflow because you'll take a negative number and a positive number and you'll end up somewhere in between. So it's guaranteed to be representable. So the danger is by adding two positive numbers that becomes too big or two negative numbers that become too small. Those are the two possible overflow cases. And as it shows, they sort of represent these little triangular regions. And also, as the formula shows here, when you do have negative overflow, then it becomes a positive number, and it has the effect of adding the value 2 to the w to the sum. And similarly, if it's a positive overflow, it becomes a negative number that you can think of as subtracting 2 to the w from that number. So I think the only example here was one that didn't overflow. So if you wanted to do it at the bit level, you'd have to take some other examples. Okay, so that's addition. And I should mention, by the way, again, if we just go strictly by the C programming standards, they guarantee that unsigned arithmetic is always modular, but they don't guarantee what happens if you overflow either positive or negative with signed addition. So if you're really, really strict and careful about how you do C programming, you should guard against any case like that. Again, in practice, it's this 2's complement representation. So there's a very predictable behavior of overflow or underflow, overflow either positive or negative. But it might not be what you want. So, but you can at least predict what it is. So multiplication is a little bit messier. Again, in this big pile of stuff, what it basically shows is if I have two numbers that are each W bits, and I multiply them, then I should need twice as many bits if I want to safely represent the product. And that result holds for both the unsigned case and for the 2's complement or signed case. And basically, you can take the largest number you represent, you square that, and that will require two times W bits to represent. But again, we don't have arbitrary, we can't just keep adding bits to our numbers in general to do this. And so what happens is we just truncate the result. So for example, with unsigned, if you had two operands, U and V, and you multiply them, you might need twice the number of bits to represent the true product, the sort of mathematical product of those two numbers. But we'll just drop off those upper bits and just leave the result within this W bit range. And again, you can see that this is exactly an implementation of modular arithmetic. And modular arithmetic is something that's maybe not the standard multiplication, but it's one that people know and understand very well. So again, if I took my two numbers, 226 and 213, and multiplied them, I'd get 47,499, which is too big to represent in 8 bits. So I just chop off those upper bits, and I get 221, which is the mod 256 product of these two numbers. Sign multiplication is a little bit trickier, actually, it turns out. It turns out that to actually, when you do 2's complement multiplication, again, you should use, your product will be twice the number of bits. And if you look at the bits, they'll actually be different than they were for the unsigned case. So look at the example here. You'll see that to multiply these two numbers, two negative numbers, you get the positive result 989, and its bit level representation looks like so, 0. And if I go back and look at the same bit pattern being multiplied as an unsigned number, you'll see a different bit pattern for these upper 8 bits. On the other hand, if you look at the lower 8 bits, 1101 and 1101, you'll see that's the same for both the signed and the unsigned case, 1101, 1101. And so, and this is actually an important rule, is that the lower part of the product, which is typically the only part that you keep, is the same whether it's a 2's complement multiplication or an unsigned multiplication. The upper bits can differ, but it's relatively seldom that you actually want the full sort of twice the size product of two numbers. So for example, in x86, there's some special instructions you have to do to get that product. The normal multiply instruction only gives you the lower 32 or 64 bits. And it takes a special instruction to get a full 64-bit product of two 32-bit numbers or 128-bit product of two 64-bit numbers. And so, so most of the time, then, the fact that the lower parts of the bits are the same is good enough to say, okay, I'm going to use the same multiply instruction for both cases. And we'll see with x86, they actually have two different instructions for doing the larger version of multiplication when you need the full representation. So one of the things you'll see, one of the things we do in this course that's kind of unusual is that we look at we'll write C code and then look at what a compiler spits out when it compiles that code. And one of the realities that you have to deal with in doing that is looking at code that the compiler has done some optimizations that you have to learn what those optimizations really mean. So an example of that is anytime in C you have an expression that involves multiplying by a constant, and especially if that constant is the power of 2, then the compiler would actually stick a multiply instruction in there. It will stick in a shift. And the reason is that if you want to multiply by a power of 2, you can do that by just shifting the number left, the appropriate number of bit positions. So if I want to multiply a number by 2 to the k, but then all I have to do is shift that number left by k positions. And you remember the shift always has the effect of filling in on the right with the zeros and dropping off any bits that fall off the end. So both of those cases, even when it sort of overflows as a result, it's still preserving the same arithmetic behavior as a multiply instruction would. And you can think of it, again, if you think about how these numbers, remember if it's we'll just think of unsigned for now. When we shift that number up, what we're doing is each bit now has a weight that's 2 to the k greater than it would have if it had stayed in its original position. And so we're giving all these bits sort of an extra boost, and that has the effect of multiplying the whole number by 2 to the k. And again, the rule says whether it's signed or unsigned, we can just drop any bits that get shifted out, and we'll get the same effect as if we'd done the sort of regular bit level multiplication operation. So for example, if we shift a number left by 3, it's the same as multiplying it by 8. And you can put together various combinations of these. Like if you shift a number left by 5, that's the same as multiplying it by 32. And then you subtract off shifting that same number left by 3, that's like multiplying it by 8. So since 32 minus 8 is 24, that's the same effect as multiplying the original number by 24. And you can see you can mix and match these because multiplication distributes over addition. It has, even in this sort of strange world of 2's complement numbers and unsigned numbers in modular arithmetic, it has that same set of arithmetic properties. And so even if there's overflows or funny things that happen, this equality is still the exact same. And that's why the compiler can safely replace a multiply by 2 shifts and an add, and be sure that no matter what the number is, it will have the same result. And it depends, actually. It depends on the hardware whether that's a good idea or not. Is 2 shifts and a subtraction faster or slower than a multiplication? That actually depends on how fast your multiply is, right? And how fast it can perform the other instructions. And I think the processors you'll find today, it's about a dead heat on those two. They're pretty close to each other. And the compiler doesn't actually know much about your real hardware, it's just making a guess. But it will typically do these kind of substitutions. Questions?
When you multiply and overflow, is that undefined in C?
Yes. If it's unsigned arithmetic is guaranteed to be like modular arithmetic, both multiplication and addition. Signed numbers, right, just like addition, there's no, the standard does not specify it has to have a certain behavior. I have to kind of keep reminding myself of this because I've gotten a bit sloppy at times. So say, it's just too complicated. I know how that works. So here's another trick that's kind of an interesting one, and if you like this kind of stuff, and that actually is very useful too, is if you want to divide by a power of 2, you can do that by shifting as well. And for the unsigned case, it's very straightforward. If you want to divide by 2 to the k, you just shift the number right by k bits. And this can be pretty useful if you want to scale, like you want to ask, how many bytes, given some number of bytes, how many double precision numbers can I stick in there? You want to divide it by 8? Well, you just take that original number and shift it right by 3 positions, and that gives you the answer. So in unsigned, we can do this using the logical shift, which you recall fills in with zeros. And again, the sort of logic behind this is, as I mentioned, I think, on last lecture, we can think of a bit level representation, even including fractional numbers. But no longer do we have a decimal point. What we have is a binary point. And the numbers to the right of the binary point have fractional values: 1/2, 1/4, 1/8, 1/16. So if we shift a number by k, it's like moving the least significant k bits to the right of the binary point, which now all has fractional value and sums to something less than 1. So if I just now throw those bits away, what I'm doing is rounding that number down to the nearest integer, which is exactly what you want for division. So just to illustrate that with some examples, you see that if I take the number 15,213, if I were to divide that by 2, I'd get a fractional number, 7606.5. But I want to round towards 0 in this case. And so if I just drop off that 0.5, I'll get 7606, which is what I want. And similarly, if I take 15,213 and divide it by 16, I end up with a number that 950.8125, which I want to round towards 0 to 950. And so you can see that shifting, just discarding any extra bits, has the desired behavior of rounding towards 0. For 2's complement numbers, you almost get the same result by shifting, using an arithmetic shift, and that's why the arithmetic shift is there. The only problem is it doesn't quite do the right thing with negative numbers. So let's see if I can give an example. So the idea is the same, that remember arithmetic shift, we fill in by copying the most significant bit over and over again. So you can imagine for positive numbers, it's just the same as what we saw before. For negative numbers, you see that it doesn't quite do the right thing. So for example, if I take minus 15,213 and I divide it by 2, I get minus 7606.5. Now if I just throw away these bits here, the problem is those bits had a positive value. And so what I'm actually doing is decreasing this number, or what they call round it toward minus infinity. I'm rounding it to a more negative number, which in this case was minus 7607. And similarly, you see this minus 950.8125, it's rounded to minus 951 if I just do the shift on its own. I don't do anything else. So it's not quite right. It's off by 1, basically, for all these negative cases. I want to round to 0, so I want to round positive numbers down, negative numbers up. So the trick is, and what you'll see the compiler does, is to basically take the case of a negative number and bias it by adding a little bit to it before it performs the shift. And that little bit that it adds will be just enough to kind of tip it and make it round in the right direction. And the way it does that then is by adding this bias of, let's see if I can show it. Yeah, let me just show it with the picture. By adding the number that's actually 2 to the k minus 1, which is a number that has all ones for these lowest k bits. And what that has the effect of doing is, when I add that, is I will, if this original number was all zeros, which is what's shown here, and I add a bunch of ones to there, nothing's going to happen. I mean, it will end up with all ones, but this yellow part will stay the same as before. And when I shift that and drop off anything to the right of the binary point, then I'll get back just the original shifted number, and you'll see I'm doing an arithmetic shift. I'm filling it with ones. So for the case where no rounding is required, then what this shows is this biasing has no real effect. But for the case where I needed to do that little bit of rounding, what happens is by adding this bias in here, if there are any 1 bits at all to the right of the binary point, of what will become the binary point, then this value will cause an incremented value in the yellow portion. And then when I shift that to the right, what I'll get is effectively incrementing by 1 this number, which gets my bias right. So this is probably easiest understood by example. No, this is not an example. This is best understood by example, and I don't have one handy. So this is a pretty quick march through it. The book covers this with some actual examples, and I recommend you look at those. But this is, again, so it turns out that this is always a good idea for the compiler. If it can get away with a shift instead of divide, that's a big savings, because divide is a relatively expensive operation, even on a modern processor. On the other hand, whereas I could mix and match these, I could multiply by 24 using 2 shifts and a subtraction. You see, it doesn't really work when you want to divide by something other than a power of 2. You can't sort of break that up into a bunch of separate power of 2 cases. So this is really only useful for the special case of dividing by a power of 2. But you'll see this in real-life code. So just a few other tricks of the trade. One is when I took a course in logic design many years ago, I learned this trick for computing the negation of a number in 2's complement form that they call complement plus increment. So let's see if I've got examples. Yeah. So for example, if I wanted to complement the number 15213, or increment, negate it, you see that's its binary representation. So if I complement that, if I take all the bits and just bit by bit put the opposite value in, that's complementing it. And you see numerically that represents the value minus 15214. And the intuition of why that's true is if you add x and its complement, you'll get a number that's all ones, which of course you recall is the representation of -1. And so we can see that the number x plus its complement is -1, and therefore if I now add a 1 back to this complemented number, I'll get -x. So if I now increment that, in this case it was an even number, so all I have to do is set that bit to 1, then this will be the value of minus 15213. So that's a pretty handy trick. And again, all of these it really, there's not some magic new knowledge here. They all stem back to that original formula showing what the numeric value is of a two's complement number. And so some special cases, like for 0, if I complement it, I'll get all 1s, which is -1. So if I add back a 1 to that, I'll come back to 0. And one of the interesting numbers is if I complement it, is T min. If I complement it, I actually get T max. And if I add 1 to T max, what do I get? I get T min back. So I took the most positive number and I added 1 to it, and I got the most negative number. That's what they call positive overflow. And so what you can see is actually, if you compute the expression minus x, and x is T min, you'll get back T min. Just like if you minus 0 is 0, or minus T min is T min in two's complement, in the world of two's complement. Which, by the way, whenever any question comes up, is this behavior always true or false? Usually you want to test the special cases of 0 and T min to see, because they're often the counterexample to any general rules. So just to summarize that part then, actually what I'm gonna summarize it, but we're about to do our quiz. And so if you want to start working your way into Canvas, go ahead. Because I know it takes some time with all your authentication. Oh. I'm trying to figure out how to get to Canvas. What's the problem with this thing? Are you guys taking this quiz? You're probably ahead of me. I can't use this stupid computer. Oops. Okay, let's see how we've done. Sorry it took me so long. Okay, so I'd say people generally did pretty well here. So actually the answer to the first problem was already stated in lecture. When you have two numbers with opposite signs, they can never overflow. Remember I said if it's a positive number and a negative number, you're adding them together, you'll end up somewhere in between. Most people got that. Everyone basically got the idea that shifting left by 4 is the same as multiplying by 16. Remember, it's a left shift, not a right shift. And how many values does C have for faults? It's sort of a trick question in that, remember, false has one value, which is 0. True is anything that's non-zero. This one actually was, I can see that people didn't necessarily guess the answer on this. And so we'll actually cover that in just a second. But this is good. I think this is very useful information. So I think a lot of people recalled from last time this example of a loop with an unsigned loop index I. And the problem with this is that if I is, since I is, let me start this up. Since I is unsigned, it will always be greater than or equal to 0. And so this loop test is useless. And it can be a little more subtle, as people saw, if delta is size of int. Delta is defined to be an unsigned number. And so by the rules we had, this would be cast to unsigned and therefore always be greater or equal to 0. So the particular quiz problem, let's see if this works. What it was doing is, instead of using size of int, it had a particular hex number. I think it was 48, right?
It was just 4.
4? Okay. I'm going to try this. There's a way I can change this. I'm just going to do this. And so I think some of you said, whoa, hex numbers, that looks kind of unsigned to me. And so you guessed that that would also be an unsigned number, which is not a bad guess, but it's wrong. In this case, since 4, there's actually a pretty complicated set of rules that when you write it, some digits out, what data type does that imply? And in fact, if you really want to get into this, there's a web aside for the book that you can get to off of the book's web page that says, how do I write tmin? and it goes through the whole conversion rules, which are really arcane, and it actually depends on which version of C you use. So this could be a very complicated answer, but the simple version is, if the number can be represented as an int, and there's no little u next to it, it will be treated as an int. And so hex 4 is the same as decimal 4 in this case. It will be a signed number. And so since I in this example, the example is very similar to this one, will be all this will be done using signed arithmetic. So the people who got that wrong, it wasn't like a fundamental misunderstanding. It's just there's this one kind of corner of the C rules that we didn't even cover and aren't often covered in any standard presentations. Good? So I used to counsel people, I'd say, well, if you're going to count down, then don't use unsigned arithmetic because it will get you in trouble. And there's a fellow that, I don't think he's there anymore, but used to work at the Software Engineering Institute who sent me email saying, by the way, you gave really bad advice. So this guy named Robert Secord has written a set of books about what he calls secure coding. And if you really want to be a super careful programmer, it's a pretty interesting collection of books. He has it in C, C++, he has ones in Java and so forth. And he's a computer security person. And so he's trying to say, how can you write code that on any compiler, on any system, is less prone to being attacked or vulnerable, have bugs in it. And so what he claims is that the best way to do counting down then is to use a unsigned value as your loop index, but then rather than checking is it greater than or equal to 0, you actually check is it less than your starting value. Because the logic behind that, you keep going until that happens. Because what happens is once I goes to 0, then the next thing it will become is it will wrap around and become U max, because its unsigned arithmetic is guaranteed to be modular on any machine on any compiler. So you're guaranteed once it goes below 0, or apparently below 0, what it's really going to go is up to a really big number. And so that's a very non-intuitive looking loop writing scheme, is to put, instead of greater than or equal to 0, you say less than count. And I've started using this in my own programming, and once you kind of get used to it, it looks reasonable, but at first it seemed like a very strange thing. And he even recommends, instead of declaring it as an unsigned, that you declare it as this data type size t, which is, depending on the machine type, it's always sort of a big enough number to handle the full word size of your machine, 32 or 64 bits. So that's just one piece of advice I'll pass along to you from Robert Secord. So other uses of unsigned, as I mentioned, if you really, really want to be careful, the good news about unsigned is it does have a complete specification of what to do even in overflow cases. And often modular arithmetic is actually fairly useful if you want to do multi-precision arithmetic. You saw when you were doing set operations, it's sort of natural just to think of the bits as bit flags and no sort of negative numbers involved. And you'll find in systems programming, when you talk about addresses or masks, collections of bits and things, unsigned is a fairly sort of a reasonable thing to conceptually. So it's interesting, like Java does not have unsigned numbers, but it has, because they didn't want to get into all these quirks. But in C, unsigned numbers are kind of built in and they're very useful. Okay, just to finish it up then, let's talk about how we can lay out collections of bytes in memory. And when we look at the actual machine code, assembly code, you'll see that it's issuing all these addresses. And people ask, well, where's the memory? And the answer is, well, conceptually, the memory just exists. It's called virtual memory. And it's just, you can think of it conceptually as just a big array of bytes from over a wide range of addresses. Physically, what happens is the combination of hardware and operating system software makes that virtual memory real by using some combination of caches, of actual DRAM on a typical machine, and even on the disks or solid-state drives that built into your machine, even over the network potentially, to sort of provide you that memory and swapping it in and trying to make it look like it's all really there, even if it isn't. So anyways, but from a machine level programming, we don't think about all that memory hierarchy. We just think of it as in terms of virtual memory. So you can just think of it as a big array of bytes. And in fact, when you're running multiple programs on the machine, on the same machine, they each have their own separate collection, range of virtual addresses. And what that means is if you're running multiple programs, an action by one won't directly affect the behavior of another. And that's a good thing, because if one program misbehaves, it's got a bug, it can't make the rest of the programs crash by just doing a write to some memory location. So that's sometimes referred to as a process. When you have a process is the execution of a program on a machine. And you can have one program of which there's multiple processes running that same program. So each process and each executing program has its own virtual address space. And you'll often hear people talk about word size. As I mentioned in the first class, there's no real solid definition of what a word is on a machine. We talk about 32-bit machines and 64-bit machines, but most machines, that your laptops, your phones, and most desktop machines nowadays can run code either compiled for 32-bit execution or for 64-bit execution. So it's really a combination of the hardware and the compiled code that defines what word size is. But in general, for a machine, the sort of broadest concept of a word is how big are the addresses in that machine. So, and as I mentioned, that can actually depend on the mode the machine is executing. So a 32-bit machine means that its largest address is 32 minus 1, and that's roughly 4 gigabytes. The machines that even phones nowadays are mostly running 64-bit processors. And what that means is, in principle, an address can be as many as 64 bits. And that would give you an address range of something bigger, like 10 to the 19th bytes, which is a lot of bytes, by the way, an exabyte. So you think of the biggest disk drive you can buy nowadays is, 8 terabytes or maybe bigger. But that's still 1,000 times smaller than addressable range. So to really support a full 64-bit memory space, you need a machine with, say, 1,000 disk drives, just to even have that many bits of memory somewhere. So what happens is on the machines that they actually build today, the hardware, it's not only 64-bit addresses, but they only let you use the first 48 of those. And so they don't really support true 64-bit execution. Anyways, the point being that depending on how big your words are, that defines how many bytes of memory you can address. And the general rule then is if I have a multi-byte quantity, what's its address? What's defined to be the lowest numbered byte in its collection of bytes. So we'll represent a 32-bit quantity as 4 bytes, and the address of that 32-bit quantity will be the least significant, or not the least significant, the byte with the lowest numbered address. And similarly for other sizes. And as I mentioned some previous lecture, we've seen this slide before, that depending on whether you're executing a 32-bit program or a 64-bit program, some of the data types will change. And particularly a pointer, an address, will change between being a 4-byte quantity or an 8-byte quantity. So there's one thing that's left here, is if I have multiple bytes representing a value, what order should they be relative to the addresses? And there's two obvious conventions. One is you put them in from least significant to both, and the other is from most to least. And as you can imagine, in any case where there's a choice, where then some people choose one way and some people choose the other. And so that's sometimes referred to as the byte ordering. And it's commonly called big endian versus little endian byte ordering. And that's a term that goes back to the book Gulliver's Travels, even though that was written long before there were bytes to store in a computer. And there's a fellow who wrote a kind of amusing tale about how people were fighting about this byte ordering, the way the characters in this book had fought over which end of an egg should you open. Anyways, nowadays, it turns out that you're going to live in a little endian world. If it's an x86 hardware, and that, remember, that applies to Windows, OS X, and to Linux, it's going to be little endian. An ARM processor, like is in most of your phones, can actually run the hardware can run with either byte ordering, but when you're running any of the common operating systems, it will be little endian ordering. So little endian means that the least significant bytes come first. And there's a few machines that you're less likely to encounter that are big endian, but one of the annoying things, some reason when they're designing the internet protocols, they said, whoever was in charge said, I want big endian, and they did it. So when you send packets over the internet, what has to happen, and you'll see that when you write this code, you have to use special functions to convert the byte ordering going out to the network and coming back in. So what do I mean by this? So again, assume we had a value that we wrote in hex, a 4-byte value, which we'd write, when we write it, of course, like up above, we put the most significant byte on the left and the least significant byte on the right. But now when we load that into memory, we'll see that in big endian order, if we read from left to right, it looks the same. Because the least significant byte is at the highest address, the most significant is at the lowest address. But if we write it in little endian ordering, it appears to be reversed. I mean, remember, these conventions of how you read things, list things left to right is just a convention. It's not really, the point being the address, the lowest numbered address has either the most significant byte or the least significant byte. But we'll find in the real world, since we're going to live in a little endian world most of the time, that we're often looking at things written backwards with the byte ordering reversed. So there used to be machines actually on campus made by a company called Sun Microsystems, which was later acquired by Oracle. And they're still making these machines, but they're not very common, at least sort of outside of the world of database machines. But so I could actually run these experiments and see, verify what order you'd get when you listed various numbers in a single byte order. And so if 15213 has a hex representation 3B6D, on an x86 machine, you'll see the least significant bytes is 6D, and then the next one is 3B, and then it's 2 zeros. And on one of these Sun machines, you'd see it reversed order. And on a 64-bit machine would be in a Little Indian machine, but a 8-byte for a long. And you can actually write code, and there's code actually included in the code for today's lecture that lets you sort of print out the byte representation of different data types by just sort of walking through them one byte at a time and printing out each byte value. And you can run it on various different things and get numbers like this is 15213 printed on a Linux machine, and you'll see it's a Little Indian machine. Unfortunately, I don't know any machines on campus that at least I have the count on that's a big Indian machine. There might be somewhere in the accounting department, but not otherwise. And I don't think even there. And another point that this slide makes is pointers are simply addresses. They're just, you can think of it as an index into this array of virtual memory. But where they're located, where a particular address is located, depends on the machine, the operating system, the compiler, a bunch of different things. And so from one machine, one execution to another, pointers might change values. They don't have any sort of uniform representation. And then another important part is strings, at least in C, are always represented by just a sequence of single byte values in the so-called ASCII format, where the final byte then is 0. And that's completely independent of byte ordering because it's on a byte-by-byte basis. So in fact, when you're writing software that has to be compatible across machines, one thing people often do is instead of encoding numbers in binary and worrying about byte ordering, they encode them as numeric as strings, send the string and convert back to a numeric representation. So, for example, one of the things you'll start doing in the next lab is staring at a lot of disassembled code. It's really machine code written in a somewhat human-readable format. And you'll see on an x86 machine that all the numbers are written apparently backwards. And it's annoying because it's not really backwards. It's sort of a backwards with pairs of hex digits. So 12 AB becomes AB 12. Okay, let's just finish up with a not online quiz, with just some questions. And again, these are, first of all, really great exam problems, but also good ways to kind of make you think through the implications of some of these ideas. And a lot of this we've sort of looked at in various forms. So, and the answer to these is either yes, it's true, or no, there's at least one case, one value of x for which this is not true. And in the latter case, it's good to be able to give an example. So if x is less than 0, is 2x less than 0? No, not x squared, it's x times 2. And by the way, as I mentioned, tmin is always a good counterexample generator. Yes?
Depends.
Yes, so if it depends, then the answer is no.
No, it's not true.
Right.
It's not always true.
And can you give me an example?
Let's go tmin.
Let's go tmin. That's a great example, right? Because tmin, if it's 1, 0, 0, 0, remember, multiplying by 2 is the same as shifting it left. And so I'm just going to throw away that 1. And you have to do my handwriting recognition to understand. But it became 0. So yes, you're right. How about an unsigned number, ux, is, and assume these are sort of arbitrary numbers. Is it always greater or equal to 0? Yeah, it's unsigned. Okay, this is getting more obscure. And this is a 32-bit number, assume. So if I take the AND of x and 7, and then I see that it's 7, and then I shift that number left by 30, is it going to be negative? Go, what? So what this means, you remember 7 as bit representation. Man, oh man, it's hard to write on this side. Sorry. 7 looks like 1, 1, 1, right? So x and 7, if I get 7 out of that, it means all the low 3 bits of x are 1s. And so if I shift it left by 30, I'm guaranteed that these 2 bits will become the most significant bits of that shifted result, right? And so this bit, in particular, is a 1, and so the result will be negative. So the answer to that is yes. The reason why involves very specific parts of that question, right? Is ux greater than minus 1? So the answer is no, but it's not for the obvious reason, right? So what's a counterexample to this? So first of all, what will be anything that is not the right answer? That's the non-intuitive part. Tmax won't work. But you're getting closer. Remember, ux is an unsigned number. So first of all, when I do this comparison, you remember from the last lecture, what will be the comparison type? Will it be a signed comparison or an unsigned? Unsigned, very good.
I was going to say that when you're comparing an unsigned to a signed, you convert the signed to an unsigned, and -1 is just 1, 0, 0, 0, 0.
Yeah.
So,
yeah. Well, no, -1 is all 1s.
or that.
Yeah, -1 is all 1s, which becomes u max. And so this is almost never, this is actually never true for any value of x, ux, right? But that's right. The thing to remember is, an unsigned, a signed, convert them both to unsigned. If x is greater than y, is minus x less than minus y? What would be an example? Of where this is wrong. It's actually almost true. So you have to think of the sort of less common case where it's wrong. And what did I say about good counterexamples? Yes. Yes, when y is t-min. Very good. Because when y is t-min, then minus y will also be t-min, right? And no number is less than that. So anything where y is t-min will be false. Very good. Is x squared always greater or equal to 0? Actually, I showed that in the first lecture. No, 40,000 squared is not greater or equal to 0. In general, you can have overflow cases. If x and y are both positive, will x plus y be positive? No, right? Overflow case. if x is greater or equal to 0, will minus x be less than or equal to 0? Actually, this one's true, right? But if x is less than or equal to 0, will minus x be greater or equal to 0? Well, you guys are catching on. Just use your friend T-Min and you'll keep going, right? If I, this is really obscure. If I look at x and minus x and I OR those together and shift it right by 31, will that equal minus 1? This is arithmetic shift. What works for T-Man? This actually almost works. Can you give me one example where it doesn't work? 0, yes. This might be a useful hint in one of your puzzles coming up. Is shifting an unsigned number right by 3 the same as dividing it by 8? Yeah, right? It's unsigned, remember. That was the point. Unsigned, you can just shift it. For a signed number, well, I think the shaking heads from before were for this one. No, because it might round the wrong direction. Okay, so that's... and the other one is sort of obscure. So anyways, very good. I think you're catching on to this quite well. We'll see you next time. Did a lot?